Okay. So in chapter 2, we just discussed linear differential equations of first order. Well, actually, not just first order, but linear equations. We talk about the techniques in solving first order differential equations. In this chapter 3, we're going to talk about linear models, or all kinds of models, not just linear. So the applications of differential equations in real life, that's for chapter 3. So we just use the techniques we covered in chapter 2 to solve those problems. Okay, so the first section is linear models, 3.1. Okay, so these are linear differential equations. That means in real life that we can model, real situations by linear differential equations. And the first model or problem is called growth and decay. I think we talk about that in chapter 1, maybe some models, but we didn't solve them. So we're trying to solve these actual problems presented in chapter 1. So when we talk about the growth and decay, we have growth of population, for example, and decay of some isotopes, carbon-14, like, all of those phenomena can be modeled by linear differential equation dx over dt equals kx. Like the population, the rate of change of the population is proportional to the population itself, or the rate of decay of isotope is proportional to the amount of the isotope. Okay, so here k is a constant that can be either positive or negative. All right. And we know how to solve this simple differential equation. This is a separable equation. And then the initial condition is given by x at t0 equals x0. So like the initial population or the initial amount of the substance or the isotope, then we can solve this initial value problem easily. All right. So let's do some examples. And a culture initially has P0 number of bacteria. So that's the bacteria, talking about bacteria decay. Okay. Or population, if you want. So at T equal to 1 hour, the number of bacteria is measured to be 3/2 P0. So it just splits, how the bacteria grows, it just splits. 1 splits to 2. So the number of bacteria will increase with time. So after 1 hour, it becomes 3/2 P0. Initially, it has population of P0, but after 1 hour, it becomes 3/2 P0. So if the rate of growth is proportional to the number of bacteria P of T present at time T, okay. So that means this bacteria population changes governed by this differential equation, okay? And we need to determine the time necessary for the number of bacteria to triple. So how long does it take for the population becomes 3 times of the initial population, all right? So the model we have is here. So we just solve it using the initial condition, okay? So if we use P for the population of the bacteria, then dP over dt equals K times P. And the initial condition is P of 0 equal to P0. All right. So this can be easily solved by a separate equation. Okay. So we can rewrite the differential equation as dP over P equals K dt in differential form. Okay. The original equation was in derivative. So then you just integrate the equation on both sides to get an LMP equals KT plus some arbitrary constant C. All right. We usually should get the natural log of absolute P if you integrate one over P. But since the population P is always positive, so we don't have to worry about the absolute sign here. So if you take the exponential on both sides, you're going to get a P equals e to the KT plus C, or e to the KT times e to the C. So now using the initial condition, P of 0 equal to P0. So just plug in 0 for T and P0 for P. So we get the, P0 equals e to the K0 times e to the C. All right. That's a standard procedure to solve an initial value problem, remember? So we get e to the 0 times e to the C, but e to the 0 is 1. So we have e to the C equal to P0. So we just determine this arbitrary constant e to the C. And that's just P0. So we can write down the solution to the initial value problem as P equals e to the KT times P0. Okay. Just replace e to the C by P0. Okay, so that solves the problem, but still we don't know what the K is. We know K is a constant, but we don't know the exact value of K. So that requires the condition in the problem at the T equal to 1 over P is 3/2 P0. So we can use that to determine K. So then you just plug in 1 for T and 3/2 P0 for P in the solution. So we get 3/2 P0 equal to e to the K times 1, T equals 1, remember, times P0. So that's just the e to the K times P0, and you can cancel P0 on both sides to get the 3/2 equal to e to the K. So you just take a natural log on both sides to get a K. So K is just the natural log of 3/2. Okay. So now we can plug in natural log 3/2 for K in the original solution of P. So we get P equals e to the natural log 3/2 times T times P0. Okay. So now that's the solution to the specific problem. So we determine everything. So now we can answer the question. We want to know when the number of bacteria to triple. So that means P will be 3 times P0. Okay. And then we need to find out what T is. Okay. So just plug in 3P0 for P in the solution. So we got 3P0 equals e to the natural log of 3/2 T times P0, and you can cancel P0. So we get 3 equals e to the natural log of 3/2 T. And then, well, what I can do is just take a natural log both sides. So you get natural log 3 equals natural log 3/2 times T. Okay, remember when you take the natural log of exponential of natural base, you just get the exponent, all right? So that means T is just the natural log 3 over natural log 3/2. If you use the calculator, you're gonna get 2.71 hours. Okay, so that's the whole problem, and that's the final answer. The problem itself, the differential equation itself is simple, but you have to use all the conditions to figure out all the constants in this problem. Any questions for this simple example? Okay, not very complicated, right? Okay, so that's one problem, one example. So the next example is called half-life. Okay, so that's still a linear model. Okay, we're talking about the decay of isotope. So in this differential equation describing the decay of isotope, A is the amount of the isotope at time t, okay, any time. And the K is constant again, but that's negative because the amount of the isotope decreases, it decays. So dA over dt change, is negative. So K will be negative. Okay. But again, the rate of change of the amount of the isotope is proportional to the amount of the isotope at any time. And we still have the initial condition, and we need it, of the initial amount of the isotope is A0. So A of 0 is just equal to A0. That's given. So then, we can solve this problem completely using this information. So let's just do one example about half-life. What it means is, when we talk about decay of isotope, there is a term that measure how fast the isotope decays. That's the half-life. It turns out it takes always the same time for the isotope to decay to its half amount. From now on to its half amount, it takes 100 years, for example. Then when you measure the amount after 100 years, and it takes another 100 years for the isotope to decay to the half at that time. Okay, so at any time, if you measure the amount of the isotope, it always takes 100 years to decay to its half amount at that time. Does it make sense? If you for the isotope, it always takes the same amount of time to decay to half amount if you measure the amount of the isotope at any time. It really doesn't matter when you measure it. It takes the same amount of time to decay to the half amount. Is it clear? All right. So, so that's the half-life, and it's important concept. Okay. So in this example, the radioactive isotope of lead, Pb209. If you to chemistry, then this is just the element. And this lead decays at a rate proportional to the amount present at time t. So that's basically the differential equation telling us. And it has a half-life of 3.3 hours. Okay, so that's given. So if 1 gram of this isotope is present initially, how long would it take for 90% of the lead to decay? Okay, so we know this differential equation, and we know it's half-life of decay. Okay, so we should be able to figure out this constant K by using this half-life. Okay, we're going to show how we do it. Then we can answer the question, how long does it take to decay 90% of the isotope? All right. So any questions about this problem? So let's just start from the initial value problem to solve it, and then we just use the conditions to, find out this constant K. Okay. So just solve this initial value problem again using the same procedure we did in the previous example. First, you just rewrite the differential equation in the differential form. So dA over A, it should be A, not P. I'm sorry. Okay. That's a typo here. So that's equal to K dt. Okay, again, I don't know why I got so many typos in here. So, but then you just integrate on both sides. Okay, dA over A equals K dt. Just integrate on both sides. So we got a natural log of A equals KT plus C. C is arbitrary constant that we need to determine. Once again, we don't have to worry about the absolute sign. When you integrate 1 over A, you should get natural log absolute sign, but because the amount A is always positive, so you can skip that or ignore this the absolute sign. If we take the exponential on both sides with space E, we get A equals e to the KT plus C, or e to the KT times e to the C. Remember, if you have a summation in the exponent, that's actually a product of two exponentials. So now using the initial condition A of 0 equal to A0 to determine this C or e to the C. So plug in A0 for A and a 0 for T in the solution. We get A0 equal to e to the K times 0 times e to the C. Again, K times 0 is 0 and e to the 0 is 1. So that's just e to the C on the right side. So that means e to the C is just A0. Okay. So then the solution to the initial value problem is just A equal to e to the KT times A0. Okay, e to the C is just the A0. So that's pretty much the same we did as in the previous example. Now we're going to use the half-life to determine this constant K. Okay. So what it means by half-life, it means when T equal to 3.3, so after 3.3 hours, the amount A becomes half of the initial amount. So that's half A0. So if we plug in 3.3 for T and half A0 for A in the solution, then we can find out K. Okay, so if we do that, we're going to get the equation half A0 equals e to the K times 3.3 times A0. So once again, cancel A0 on both sides. So we got half equals e to the K times 3.3. So you can see we can solve for K from this equation. So what do you do? Just take the natural log on both sides. So we get natural log half on the left and the K times 3.3 on the right, you know. You just get the exponent when you take natural log of a natural exponential, okay. So divided by 3.3 on both sides, we get K equals natural log 1/2 over 3.3, okay. So then now we can answer the question in the problem. So we want to know how long it takes for 90% of the lead to decay. So what it means is when 90% of the lead decayed, then what is left? Just 10%. Okay. So remember, A is the amount of the isotope at any time. So we want to know when A becomes 10% of A0 or 0.1 A0, what T is, right? Does it make sense? Okay. So just plug in 0.1 A0 for A and natural log 1/2 over 3.3 for K. Then we can solve for this T. Okay. So so we get 0.1 A0 equal to e to the KT times A0. All right. So cancel A0 on both sides. So the equation becomes 0.1 equals e to the KT. Again, I just take the natural log on both sides. We get and then 0.1 O equals KT. So K is just a 8.5 over 3.3. So if you plug in that in this equation and divide it by K on both sides, we get time T. So T is natural log of 0.1 over K, which is 8.5 over 3.3. So you can flip it in the denominator, you get 3.3 times 8.1 and 8.5 in the denominator. And if you use a calculator, you get the answer 10.96 hours. So about 11 hours. It decays 90% of the lead. Does that make sense? Any questions for this example? Yeah, hours, yeah. So we are using hours in here for the time. These are not a complicated problem, but you have to do it step by step to find out the constants, you know, and understand the problem clearly, what it's asking for, right? The mathematics is not really complicated in here. Those are linear models, okay? So the next example is called carbon dating. Again, this is the isotope decay. We can use, you know, the decay of isotope to find out the years of some ancient objects, the years of the Earth, for example, you know. That's how we estimate the years of the universe or whatever, you know, one method. So again, the differential equation is the same, dA over dt equals K times A, and the initial condition is the same. But this time we're using carbon-14 for the isotope instead of lead, okay? So what says in this problem is the half-life of carbon-14 is approximately 5,330 years. So that's pretty known. So carbon-14 is decaying slowly in nature. Okay. A fossilized bone is found to contain 0.1% of its original amount of carbon-14. Okay. Determine the age of the fossil. So in this fossilized bone, the carbon-14 has only 0.1% of its original amount. So we want to know how long it has taken. Okay, and we know the half life of the carbon-14 is 730 years. So that'd be a long time. Okay, so that means after 5,730 years, the amount of carbon-14 becomes half of its original amount. So if it decays long time, then the amount becomes only 0.1%. So it must be much longer time than 5,000 years. 5,000 years, it becomes 50%. So 0.1%, that means it has decayed many, many years, right? So, but the way to do it is always the same. So I guess I just wrote all the procedures again as the same as the previous example, so I'm not going to repeat it, but we just got the solution to this initiality problem, exactly the same as in the previous example. So A equals e to the kt times A0, okay? So the amount of the carbon-14 at any time is e to the kt times A0, which is the initial amount. Now we're going to use the half-life to figure out this k, just like the other example. Okay, so when t equals 5,730, A equals 1/2 A0. All right. So plug in half A0 for A and 5,730 for T. So we get half A0 equals e to the k times 5,730 times A0, and you just solve for k in the same way as we did. Cancel A0 on both sides. So we get 1/2 time equals e to the k times 5,730. So take natural log on both sides. We get natural log of 1/2 equals k times 5,730. So k is just natural log 1/2 over 5,730. Okay. So now we can answer the question. So we want to know the age of the fossil, or how long it takes for the carbon-14 decays down to 0.1%. So we want to find what T is when A is 0.1%. 0.1% means 0.1 divided by 100, which is 0.001. Okay, so A will be 0.001 A0, and then just plug in that in the solution to find out T. So 0.001 A0 equals e to the kt times A0. As always, cancel A0, so we got 0.001 equals e to the kt. Take the natural log on both sides, we get natural log of 0.001 equals kt. So T will be natural log 0.001 over k, which is natural log of 1/2 over 5,730. So flip the denominator, we got the 5,730 times natural log of 0.001 over natural log of 1/2. And if you use the calculator, what you get is 57,100 years. Okay, so that's the answer for the problem. So it takes 57,000 years to decay down to 0.1% of carbon-14. Good. So this problem is pretty much like the original, the other problem, the previous example. So we just did everything in the same way. All right. So that's how you determine the age of the fossil, in geology. Any questions about this example? So if not, let me just stop the recording.